So one of the things that I think is really interesting about organic chemistry is that there are tens of millions of known organic compounds, and more are being isolated and synthesized and identified every year. Now, fortunately for us chemists, the chemical behavior of every compound is not entirely unique, so we can separate them in the laboratory, or a lot of them in the laboratory. Instead, right, certain relationships among molecule structures gives us an idea about how similarly or differently the molecules behave. So, for example, in chapter 3, we learn that molecules that have the same functional group tend to react similarly. In chapter 5, we are going to develop a broader understanding of how molecules are related, and we're going to delve into the consequences of those relationships. And one of the things that we're going to talk about are molecules that are mirror images of each other. And if they're mirror images of each other, they react differently in the body. And so it's really important for medicines to be a lot of times one mirror image or the other, right? You can have some really unfortunate unintended consequences. And so what you see here is a lot of kind of mirror images. This is one of my favorite Norman Rockwell's, where a little girl is looking in a mirror and you can see the mirror image there. Alice in Wonderland, Alice falls into a mirror image world. And then just kind of some fun mirror image type things here. So let's review for just a minute. We have talked several times about stereochemistry, and we said, look, stereochemistry refers to the three-dimensional structure of a molecule. And so, as a consequence of stereochemistry, there are minor differences in 3D structure that can result in vastly different properties. Okay? So we talked about isomers. So I have this flow chart here. If a molecule has the same molecular formula but is different in some way, it's an isomer, right? So these are different compounds with the same molecular formula. Now we have two classes of isomers, right? We have constitutional isomers here and stereoisomers here. Now constitutional isomers have different names. So we learned how to name in the previous chapter, and so we can use that to figure out if these are constitutional isomers or not, right? They can have the same or different functional group, right? They have different physical properties, and different chemical properties. And we've talked about those quite a bit. Now, when we talk about stereoisomers, we've already talked about one type of stereoisomer. Stereoisomers differ only in the way the atoms are oriented in space. And so if they differ by rotations around single bonds, like we saw in ethane and butane, then those are conformers of each other. So we've talked about the things here and here. What we're going to focus on in this chapter are configurational isomers and diastereomers and enantiomers. So stereoisomers, which configurational isomers and diastereomers and enantiomers fall under, differ in only in the way the atoms are oriented in space. Okay? And so that means they're always going to have the same functional group. Okay. So when we look at this, I wanted to give you some examples of the constitutional isomers and stereoisomers. Constitutional isomers are things like 2-methylpentane and 3-methylpentane. What you see here is these differ in their names tremendously because there's a methyl at the 2 position here and then a methyl at the 3 position here. Now let's look at stereoisomers. We've also looked at stereoisomers that are cis and trans isomers of each other in the previous chapter. And so I want you to notice that if we were naming these, they both have the name 1,2-dimethyl-cyclopentane, but we know they're different and therefore going to have some different properties. And so that's one of the reasons why we say, look, this is cis and this is trans, to distinguish between 2 molecules that are different. So these have the same molecular formula and the same name except for the prefix, okay, that's been added to help us with that. Now, I want to talk a little bit about this idea of things with mirror images, okay? Although everything has a mirror image, mirror images may or may not be superimposable. And so to superimpose means to line all the parts of 2 objects, right? So when we talk about something that's superimposable, right, all parts of 2 objects align, right? And we also talk about things that are non-superimposable, right? Where not all parts of 2 objects align, right? And so a really good example of this are hands. And some molecules are like our hands. So the left and right hands are mirror images of each other, but they're not identical, right? They are superimposable. If you lay one on top of the other, your thumbs are going to be in different positions. So these would be considered non-superimposable mirror images of each other. Other molecules can look like the socks here. Socks, right, have mirror images that are superimposable. That means you can lay them on top of each other and they look the same, okay? So if you have a molecule or an object that is superimposable on its mirror image, it's said to be achiral. So let's give some words to that. So something that is achiral, and that's one word, is just a molecular object that is superimposable on its mirror image. Okay. Now, let's look at some achiral molecules. So these molecules are things that are going to be superimposable. Water is a really good example. Water has a mirror image, but when you line the 2 molecules up, they're identical, right? The bonds here and the atoms here and here and here all align or match. When we look here at CH2BrCl, there's a mirror image, but it's a superimposable mirror image. If I put these 2 carbons next to each other, I can arrange it so that the 2 hydrogens here and the 2 hydrogens here and the bromine and the chlorine all align. So this molecule is also achiral. Now, let's look at a chiral molecule. So this molecule right here and here, this is CHBrClF. This is a chiral molecule because when you line up the 2 carbons and one of the other groups, this is the hydrogen, what you're going to see is that the chlorine and the bromine do not line up next to each other. Okay, so that means that these are 2 different molecules. Molecules that are chiral react differently in the body, and so they have different properties. Okay. Now, right, A and B here are considered to be stereoisomers. Right? Specifically, this is an example of something called enantiomers that we talked about on the previous slide. And I'm going to give a definition to that later, right? And so what we find is that this molecule contains what we call a stereogenic center. And so a carbon atom with 4 different groups is a tetrahedral stereogenic center, right? So in general, a molecule with no stereogenic centers So if you have a molecule, you can have a molecule with no stereogenic centers. For example, water, right, that we just looked at. This will not be chiral. Okay. Now, like all good chemists, I'm going to say there might be an exception to this that we will consider later. But for right now, where you are in your educational journey, we're going to go with this. Okay. Then, right, if the molecule has one stereogenic center, right, it will always be chiral. Okay? And a chiral molecule has enantiomers. Then, if you have two or more stereogenic centers, right, a molecule may or may not be chiral. And we're going to look at how to figure that out in a second. Okay. So, right, I want to hone in on trying to kind of figure this out. You know, if you have two or more stereogenic centers, you may or may not be chiral. And so when we think about this, okay, I want us to talk about planes of symmetry. Okay. Now, this atom here has two of the same thing attached. So it has a plane of symmetry. That means if you divide it down the center here, you have the same thing here that you have over here. It has two identical halves, okay? It is achiral. You can have some molecules with two or more stereogenic centers that also have a plane of symmetry, right? And that makes them an achiral molecule. So, an achiral molecule usually contains a plane of symmetry. But chiral molecules do not. So chiral molecules do not have a plane of symmetry. Achiral molecules do. So I have a summary here for you because I find that it could be, my hope is that it is helpful, right? Everything has a mirror image. The fundamental question that we're asking here is, does a molecule and its mirror image, are they the same? Are they are they non-superimposable? So can you lay them on top of each other and they look exactly alike or not? So if not, right, if they're not superimposable, they're chiral and don't have a plane of symmetry. If they are superimposable, they're achiral and will contain a plane of symmetry. For me personally, it is easier for me to look for a plane of symmetry. This is very helpful. It was helpful when I was a student and first started identifying these. If something has a plane of symmetry, it is going to be achiral. And so that's a really good skill to practice. The terms that we use, stereogenic center and chiral molecules, are related, but they are distinct, right? Because you can have two or more stereogenic centers in a molecule that is achiral because it has a plane of symmetry. And then a chiral molecule has to have one or more stereogenic center. We are going to continue to look at this and practice identifying things that are chiral and achiral and stereogenic centers in the next screencast.